Swayam Prabha. Digital India. Educated India.
Today we will talk about analysis of beam with ER and MR fluid layer. Now, so far whatever we have discussed on the ER and MR fluids, they are different flow mode analysis. Those can be found in the book by Chopra and Sirohi, that is our textbook, and also the paper that we have referred to. For this discussion, where we are analyzing a beam with ER and MR fluid, we would refer to this paper, that is referred here. In some cases our way of formulation or notations can be little different from them, just so that we are consistent with the kind of formulation that we have done so far, but the example and the development of the formulation is taken from this paper. So, here we have a beam, and this beam is a sandwich beam, sandwich in the sense that it has two layers at the two sides, top and bottom, and the mid layer is different from the top and bottom layer. So, it has three layers. The top layer is an elastic layer. Elastic means it is an elastic solid. The bottom is also a elastic solid. The mid layer, at the core of the mid layer we have this red zone is ER or MR fluid, and this fluid is covered by a, I would say, a box made of rubber. So, this rubber region we can see in the cross sectional view in the XZ plane, that is at the periphery. Similarly, in the cross sectional view in the XY plane, we also it is seen in the periphery. So, this entire rubber region, which, so this is the wall of the rubber, the thickness of BR. So, that rubber region contains the ER MR fluid inside it. Now, the dimension of the beam along the direction x is L. The thickness of the solid layers are, we can call H1, H2 and H3, and then we have the here the dimensions. So, if we look at the entire system in the xy plane in a cross sectional view, we can see that the width of the wall of the rubber is BR and the entire width is P. So, when this beam vibrates, the rheological fluid, because of its damping, dissipates the vibration. So, that brings damping to it, and that damping can be controlled by controlling the electric or magnetic field in the rheological fluid. Now, in this analysis there are some assumptions. First of all, the axial stiffness of the fluid layer is negligible. That means, this mid region, the core region, it does not have any axial stiffness. The only axial stiffness comes from this that rubber region, but that is much less. I mean, the dimension of it is much less as compared to the dimension of the core fluid. So, this has negligible axial stiffness. That also means that shear normal stress is 0. So, in the fluid region normal stress is 0, and this thickness H1, H2 and H3, they are much smaller as compared to L, and they are their sum H1 plus H2 plus H3 is also quite small. So, we can have Euler-Bernoulli assumption here. So, we make Euler-Bernoulli beam assumption. There is no slip between the elastic and fluid layer, and the elastic solid, their damping is negligible, and the transverse displacement is function of x only. So, we denote the transverse displacement as W. So, W is just a function of x, and that means that the quantity W does not vary along the depth or along the width. So, with these assumptions we will do our analysis. Now, from this kinematics, first we have to define the shear stress in the fluid layer. Now, the shear stress in the fluid layer is gamma, which we can say del W by del x plus del U by del z. So, that is the shear stress in the x z plane. Now, del W by del x we know that remains constant along the cross section. Del U by del z we have to find out in terms of some quantities. So, we find out del U by del z in terms of this W as well as the axial displacement along x direction at the middle of the top layer and the middle of the bottom layer. Now, let us denote U1 as the displacement at the middle of the top layer. So, at any x U1 is denoted as the displacement at the middle of the top layer, and U3 is the displacement at the middle of the bottom layer. So, U1 and U3 are displacements at the middle of top and bottom layers. So, if it is so, then the displacement at this junction here at the end of the at the bottom of the bottom layer. So, the junction between the core and the top layer can be written as, so we can say that this is, as we know, this is as per our definition, this is H3 and this is H2, H2 plus H3. So, U at Z equal to H2 plus H3 can be written as U evaluated at Z equal to H2 plus H3 is our U1 plus H1 by 2 multiplied by del W by del x. Now, because this is an Euler-Bernoulli beam, we know that that plane section remains plane before and after bending. So, if at any section it has our 3 layers, and if it bends, then after bending it takes a form like this, because we know that based on the Euler-Bernoulli principle, plane section remains plane before and after bending. So, a displacement, if the displacement at the mid of the top layer is U1, then the displacement here is U1 plus this additional amount, and this additional amount is nothing but del W by del x multiplied by this height, and this height is our H1 by 2. Now, because we are going towards negative z, so we are adding it, because we know that u as we go up along z direction is minus z into del w by del x. Here we are going in the downward direction. So, it is this quantity is additive. So, we have u 1 plus h 1 by 2 into del w by del x. If this same quantity was to be found out with respect to this the mid plane of the entire beam, then it would be just minus of del w by del x multiplied by h 2 by 2. But here we are finding out with respect to the mid of the top layer. So, it is u 1 plus h 1 by 2 multiplied by del w by del x. Similarly, u at z equal to h 3 if we want to find out, that means here, and that if we found out if you want to find out based on u 3, then that becomes u at z equal to h by 3 is equal to u 3 minus h 3 by 2 into del w by del x. So, we have found out u at the junction between layer 2 and 3 and layer 1 and 2. So, if I want to find out del u by del z now, then del u by del z is just the difference of u between here and here divided by the thickness of that layer h 2. So, del u by del x is u at z equal to h 2 plus h 3 minus u at z equal to h 3 divided by h 2. And if we do that, then the quantity that we get is u 1 plus h 1 by 2 into del w by del x minus u 3 plus h 3 by 2 into del w by del x, and then that quantity is divided by h 2. Now, we can put this. So, this is del u by del x del z, not del x. So, if we put that this del u by del z here, that gives me gamma. So, after putting that, gamma becomes 2 into h by 2 plus h 1 plus h 3 divided by 2 h 2 into del w by del x plus u 1 minus u 3 by h 2, and then that quantity can be written as d by h 2 into del w by del x plus u 1 minus u 3 by h 2, where d is defined as a quantity which is h 1 plus h 3 by 2 plus h 2. Now, we have to find a relation between u 1 and u 3. So, that can be found out by balancing the normal forces along x direction. So, for that we can write longitudinal forces along x in the elastic layers, and those are F 1 equal to E 1 A 1 del u by del x, because we know del u by del x is strain. If I multiply that with the corresponding Young's modulus, that gives me stress, and A 1 is the cross sectional area of the first layer, the top elastic layer. And similarly, we have F 3 equal to E 3 A3 into del 3 by del u 3 by del x. So, again A3 is the cross sectional area of the bottom layer. Now, we know that there is no externally applied normal force. So, F1 plus F3 should be 0, that is our equilibrium condition, and that gives me E1 A1 multiplied by del u by del x is equal to or minus of E3 A3 into del u 3 by del x. Now, we can integrate both sides, and that gives us E1 A1 U1 equal to minus of E3 A3 U3, and then we can write U3 is equal to minus of E into U1, where E1 is defined as small e1 is defined as capital E1 A1 divided by capital E3 into A3. So, this relation helps me get rid of one of the unknowns in the problem. Now, in the problem I have two unknowns, one is W and one is either U3 or U1. So, now we will write in the formulation the unknowns as U1. So, we will consider U1 as the unknown and we define U1 as just U, and we will solve the problem. Now, before doing that, we have to write the shear stress also. Now, the shear stress, the shear modulus at the mid layer. So, mid layer has our rubber plus ER or MR fluid. Now, rubber and ER MR fluid have different shear modulus. So, we define something called equivalent shear modulus of that layer, and that we just do by the rule of mixture. So, for that we write G bar, the shear modulus at the mid layer, is equal to GR multiplied by BR by B plus G star multiplied by 1 minus BR by B. So, GR is shear modulus of the rubber that is used, and G star is the shear modulus of the fluid. Now, here we can see that BR, this is the ratio of the width of the rubber multiplied by the entire width of the rubber plus the ERMR fluid, and this is the ratio of the width of the ERMR fluid layer divided by the width of the entire beam. So, it is just the equivalent shear modulus G bar is just a weighted combination of the individual shear moduli. Here the weight is the ratio of the width. Now, for G star, which is the shear modulus of the ER and MR fluid, we use the constitutive relation that we discussed last week based on the paper by Chen and Yo. So, here we saw the viscoelastic property of the MR fluids. Here the pre-yield viscosity was viscoelasticity was incorporated in the model, and that is what we are going to use here. So, G star is, again as we saw that G star has two parts, one is G prime plus I into G double prime. So, G prime is storage modulus and G double prime is loss modulus. So, this is the same model we are going to use for the pre-yield condition, and for the post yield it is just tau is equal to tau y plus mu into gamma dot, which comes from which is the Bingham plastic model. So, this is Bingham plastic model. Now, with all these, so we have defined the shear strain in terms of the displacement, and we have defined the shear modulus. So, we can now write shear stress. Now, with all these, now we can write all the different energies, and from there we will write the variational formulation. So, we have two layers, two elastic layers at the top and bottom. Now, the strain energy of the two layers can be written as this. So, half into the integral of E1 A1 multiplied by del u by del x whole square is the strain energy of the top elastic layer. So, we are writing u as just U1, because we have got rid of U3 because of the relation between U1 and U3. Now, this is E3 A3 small e square multiplied by this quantity integrated and multiplied by half, that gives me the strain energy of the bottom layer. Now, these strain energies are the strain energies due to the extension of those layers. Now, those layers bend also. So, because of the bending, these are the strain energy. Now, these I1 and I3, these are the moment of inertia with respect to the centroid of their own centroid. So, now I1 and I3 are moments of inertia of the top elastic layer and the bottom elastic layers, and these are defined with respect to their own centroid. Because we have seen that in these three layers, if I define the moment of inertia with respect to here, then I need to define the moment of inertia of this layer with respect to its own centroid and shift it using the parallel axis theorem. If I do that, then I am writing everything in terms of the centroid of the three layers combined. In that case, these energies do not come into picture, and in that case, after shifting by parallel axis theorem, whatever the moment of inertia expression I have, that gives us, because of that I get these two energy combined in just this expression. But here, because I am writing these two layers separately, I am writing it the strain energy due to the extension of its mid layer here and the bending of this layer itself, where I is considered with respect to the centroid of this layer itself. So, that is why they are written separately. So, if I can write them separately if I take the centroid of the layer itself, or I can write it in a combined way if I take the centroid at the middle of the combination of these three layers. So, here we have written them separately. So, we have two variables w and u. So, these i's are the moment of inertia with respect to their own layer. Now comes shear strain energy of the mid layer. We have defined the shear strain at the mid layer, and we know the shear strain shear modulus, which is G gamma. So, again we do half into G into A2, and then we multiply the shear strain square, and that gives us the shear strain energy of the mid layer. kinetic energy considering motion along z of the elastic and fluid layers, which is this. So, half into mass into velocity square in the transverse direction. So, here this is the contribution from layer 1, layer 2, this is the contribution from the rubber layer. So, this is rubber density and this is the density of the ER and MR fluid. This is the density of the bottom elastic layer, this is the density of the ER and MR fluid. So, this is ER, MR fluid density and this is density of elastic layer 1, this is density of elastic layer 3. Now, we will write the other component of the kinetic energies, which is T2 here. So, these are the kinetic energies due to the extension of the layers and then we have the kinetic energy correspond considering rotation of the MR fluid layer. So, it is rotation. So, it is rotational motion. So far we have neglected the kinetic energies due to rotation, but here it is incorporated. It can be neglected also if the layer thickness is small. Now, here again I2 is the moment of inertia of that fluid layer with respect to its own centroid, and here rotation is defined as del W by del X minus del U by del Z. So, we know del U by del Z. So, we can write the rotation. So, after having all the energies, now we can make some approximation for our variables U and W and put it here, and then we can minimize T minus U, that means the total kinetic energy minus the total strain energy, or we can make a variational form and then put it in the variational form and then form a set of ordinary differential equations that we want. So, this is the variational form. If I take variation of all the energies, so we have T1, T2, T3 and V1, V2, V3. So, if I take T1 plus T2 plus T3 minus V1 minus V2 minus V3, and again we know that the Hamilton principle says that its integral over any two arbitrary time T1 and T2 is 0, and we know how to get into this kind of equations from this principle. Now, one thing to note, in so far in all the formulations we have denoted our strain energies as U1, U2, U3. Here we have denoted them as V1, V2, V3, but they are same. Now, after that the variational function variational form that we get is this, and then we put some approximation. U is approximated using a set of basis functions Q u, phi u, and W is approximated using a set of basis functions phi W u, and then if we put it there, and then we get equations of this form plus variation of Q u n u, variation of Q w 1, we have done this kind of formulation several times in this course so far. So, we know that because these are independent variations, so each of the terms in the bracket is 0, and that gives me a set of equations of this form. So, set of Nu plus Nw equations. So, in this equation the mass matrix M takes a form like this: M U U, M U W, M W U, M W W. Similarly, the stiffness matrix takes a form like this: K U U, K U W, and K W U, K W W. And here So, mu u is this, mu w is this. We can just look into the variational formulation and we can figure out the kind of forms these matrix elements take. So, this is m w w. Similarly, these are the elements of the stiffness matrix. So, this is the final set of ordinary differential equations that we got, and this is a free vibration equations since there is no externally applied force. So, the right hand side is 0. Now, this gives rise to an eigenvalue problem, because if we consider q as q 0 multiplied by e to the power I omega t and then put it here, that gives me minus of omega square m multiplied by q 0 multiplied by e to the power I omega t, because if I differentiate this quantity twice with respect to t, then minus omega square comes out, and e to the power I omega t is common in both side in both the terms. So, I do not need that, plus we have q 0 equal to 0, and then we can write this entire quantity as so, this is an eigenvalue problem. Here one thing to note is that this k has contribution from the shear in the fluid layer, and the shear modulus of the fluid layer was a complex function. So, by solving this eigenvalue problem from the eigenvalues, we can estimate the damping present in the system. For different values of the electric field, we can find how the damping changes in the system, and that kind of study can be done from this equation. So, that brings us to the end of this lecture, and also it brings us to the end of this course. I would like to thank all the participants for their interest. I hope you enjoyed this, and I also sincerely appreciate our teaching assistants Mr. Vaibhav Mishra and Professor Sani Akhtar, and I also thank the entire NPTEL team. Thank you.